All right, let's dive into something pretty incredible. We're looking at a new generation of materials that could totally revolutionize our buildings, making them safer and way more energy efficient. And it all starts with this one kind of wild question. I know, it sounds like something straight out of a sci-fi movie, right? But that's the exact idea we're digging into. A single, smart surface that can go to battle against two of the biggest threats our modern cities are facing right now. So why is this such a big deal? Well, because our buildings, the very places we live and work, are under a ton of pressure from two problems that are basically converging into a perfect storm. It's a real one-two punch. On one hand, you've got the urban heat island effect, which is making our cities dangerously hot. And on the other, many of the common materials we use to build them can make them incredibly vulnerable to fire. And a huge piece of that overheating problem is energy. Get this. Buildings are responsible for over 40% of global energy use. And a massive slice of that is just for air conditioning, just for trying to fight off the heat. And the stuff we build with, well, it's just not designed for these kinds of extremes. Concrete cracks under the heat stress. Steel literally loses its backbone in a fire, leading to structural collapse. And a lot of common insulators, like polyurethane foam, aren't just flammable. They can release incredibly toxic smoke when they burn. Okay, but this is where the materials science gets really, really clever. Instead of trying to solve these problems one by one, researchers are creating a single, elegant, integrated solution. And this slide right here shows the beautiful balancing act they're pulling off. It's a single coating that does two critical jobs at the same time. On one side, you have radiative cooling, which is actively pushing heat away from the building. And on the other, you have flame retardancy, which is designed to stop a fire dead in its tracks. So first, let's talk about that cooling superpower. I mean, how on earth does a surface actively cool a building down without using a single watt of electricity? The technology is called passive radiative cooling, or PRC, and it is an absolutely ingenious process that basically uses the laws of physics to its own advantage. It's passive, so no energy required. Now, this is where the magic really happens. It's a two-step move. First, the surface acts like a perfect mirror to sunlight, bouncing it away so the building doesn't absorb all that energy. But second, and this is the really cool part, it radiates its own heat out. And it sends that heat out at a very specific wavelength, one that slips right through our atmosphere. It's like finding an open window straight to the freezing cold of outer space. It literally beams its heat away. Okay, so that's the cooling. Awesome. But let's move on to the second superpower, fire protection. What happens when these exact same materials get hit with an open flame? Well, they fight back, and they do it on two fronts at once. In what's called the gas phase, they release harmless gases like water vapor that dilute the oxygen a fire desperately needs to burn. Then, in the condensed phase, they form this tough, protective barrier, a char layer, that physically insulates material underneath and traps any flammable gases. And this image just nails that synergy. You can see the char layer is blocking the fuel source from below, basically smothering the fire, while the gas phase action is attacking the flame from above. It's a complete built-in defense system. So you're probably wondering, what do these materials actually look like? And how do you combine two completely different properties, like cooling and fire resistance, without one messing up the other? This roadmap is fantastic because it shows exactly how we got here. You have these two totally separate fields of research. On the left, you've got the long history of developing flame retardants. On the right, the more recent, but just as exciting, world of radiative cooling materials. And the goal, right there in the middle, is to bring them together, to integrate them into these new multifunctional systems. But, it's not that easy. For example, adding certain flame retardants can make a material darker, which is terrible for reflecting sunlight. So the real trick, the real challenge, is to design a material where the two functions actually help each other out, or at the very least, don't get in each other's way. And the secret? It's all in the microscopic structure. On the left, just look at that. You can see how it's engineered to be porous and needle-like. That unique texture is what makes it so good at scattering sunlight for cooling. But that same structure, as you can see on the right, is what also helps it stand up to a direct flame. It prevents dripping and slows the fire spread. The design itself gives you both benefits. It's brilliant. So let's zoom out. We've seen the science, which is amazing. But what does all of this add up to? What's the real-world impact if a technology like this becomes widespread? I think this quote from the research really says it all. This isn't just about making one building better. It's about creating a whole new standard for architecture, one that's just fundamentally safer, more sustainable, and more resilient. And the potential scale of that impact is just staggering. Check out this chart. Widespread adoption could cut global CO2 emissions by over 1 billion metric tons every single year. And why? Well, because every building that's cooling itself passively is a building that isn't running a power-hungry air conditioner 24/7. Which really just leaves us with one final thought. We are looking at a technology that can slash energy consumption, that can save lives in a fire, and that can make our cities tougher in the face of climate change. So the question really isn't if we need this, but how fast we can start building it into our world.